see. What we're going to do today is finish off chapter 6, and then we're going to get into the design of experiments portion of the class, which is where we will remain for the rest of the class. So the last hypothesis test that we're learning in chapter 6 is the test for equal variances. So as mentioned before, that's a very common thing, is to try to do something to reduce the noise in our system. And so the test for equal variance will allow us to determine if we did indeed reduce the noise. And so in general, it's a harder thing to get a hold of. So if you think just generally, if you're talking about means and variances, it usually takes a pretty big difference in variance to be able to detect it as compared to a mean. So it's kind of hard to compare those two, but it generally takes a pretty big difference in order for it to pop up as significant. So we learned the F-test before we went through this example. So now we'll finish off the notes by going through this group problem. So what this group problem is getting at is we're manufacturing some pharmaceutical product, has some sort of sugar content, and we measured it on 3 days. And the question we're wondering is, does the variance change from day to day? And so we're going to ask 2 specific questions. And so we will need to answer these with hypothesis tests. So the variability in process day 2 and day 1. Let's compare those two. Can you say there's a significant difference? And again, if it's not given, our hurdle value based on area is going to be 5%. So please do this in groups and make sure to do all the steps of your hypothesis testing. State your null hypothesis and your alternative hypothesis in terms of Greek letters, your variance sigma squared. Any questions? How are you guys doing? These work really well when those have holes in them. They go in there. That's what I'm here for, just to help you out there. Do you guys have any questions? Make sure to write a conclusion that's more descriptive than just reject H naught, accept H1. Yeah. Pardon?
What's it asking for when it asks for the variable? Because I did this stuff from yesterday, but
Okay, that means, so the variance. So when we're talking about the variability, we're talking about the noise. The only test we have is to test the ratio of the variances. Right, the F test. All right, looks like some people are finished. A lot of people working on the second problem. Let's go over this. So we've got these three data sets, and one thing that we notice in looking at them is it seems that perhaps we had more noise on day 2 than day 1. Does everyone see that? And so we don't know for sure. Again, what we're learning in this class is this difference real or is this not real? And so we're going to do a statistical test to answer that question. So the first test, or the null hypothesis, is no, it's not real. Those two numbers really reflect the same variance. So we'd say sigma 2 squared is the same as sigma 1 squared, or sigma 2 squared over sigma 1 squared is equal to 1 or less than equal to 1 because our alternative hypothesis is that sigma 2 squared is greater than sigma 1 squared. I recommend at least the first couple times that you do that, that you write both these things, write the equals or greater than before you do the ratios, just so that it makes a little bit more sense to you. Anybody have a question about those two hypotheses? Is that what you have on your paper? Okay, good. Yeah. Yes. Yes. This is how the book does that. Some books will just say this. Some books will just say they're equal. This book is a little bit more exact, and it'll say, well, less than or equal to, but we will test it at these two are equal point, because that's the worst case scenario. So it doesn't change how we do the test, it just changes how that null hypothesis looks. So we assume H naught is true, and that's the next step, which we draw the F distribution. In this case, drawing the F distribution isn't so earth-shattering. It just looks like that for sigma squared over sigma squared equal to 1. It's the one in the book, but we can certainly draw it. Assume H naught. Then we go calculate the statistic of interest, and that's the F statistic, and that's taking our sample variances and their ratio, so 0.148. And keep in mind, the F statistic is a ratio of variances, just how it was developed, so we have to be careful and not throw standard deviations in there, make sure we're dealing with variances. And so you get 7.79 as F. And we want to figure out what's the p-value associated with that F. So we need number of degrees of freedom. So our F has how many degrees of freedom in the numerator? How many went into S2 squared? 13 data points, so this would be 12. So I'll just say new 1 is 12, and new 2 is 12. So you look that up in your book, 12 degrees of freedom in both cases. F12 of 12, we find F12 comma 12 at 0.05, or I'm sorry, you see a 0.001. You can find that number, that's pretty close. So an F of 7 would give you a p-value of 0.001. Can you see that? That's one way of doing the problem, is by finding the p-value, and that we could say our p-value then is less than that. Right? We can find that one in the table. Since our F value is bigger, our p-value will be even smaller than the 0.001 that we found in the table.
So you just find the number that's like closest to it.
Yeah, so you can bracket it if you want. So I could have done the other side as well. The F table, so look at 12 degrees of freedom and 12 degrees of freedom. Got it? Yes. Yes. That would be the other way of doing it. You could find you could use alpha as 5%, and you could get an F star. So anybody do it that way? What F star did you get? 2.69. Did anybody else do it that way? That's perfectly legitimate. Right? So this would say alpha of 5% gives a hurdle value for F of 2.69. Since our F is much greater than that hurdle value, it is a significant finding. We reject H naught, accept H1. And in the words of the problem, what would we say? Yeah, the variability on day 2 was greater than that of day 1, and then we might then take off our statistician hat, put on our engineering hat, and say, now we're going to go find out why. Okay. Day 3 greater than day 2. So maybe I'll just, well, I won't do it. I'll do it the long way. So H naught. So sigma 3 squared over sigma 2 squared. Try to write more legibly. F here 0.269.148 is a 1.82. And again, the hurdle F star is 2.69. The F from our data is 1.82. So what do we say? What's our conclusion for the second part? Can we conclude that day 3 variability is greater than day 2? No, we can't. So we fail to reject the null hypothesis. All right, any questions on that? Yeah, John. Yes, so the first part we did the p-value method. P was less than 5%, so we rejected H naught. Here we just switched up and did the compare with the F star method, but you can mix and match those. You can follow your heart on those, which allows you to kind of assert your individuality in engineering. And so we found that this 1.82 was not over the hurdle value, so we could not reject H naught. So the p-value associated with 1.82 is going to be greater than 5% if you did it that way.
The top one, F star, was less than, the hurdle value was less than 7.
Yes, exactly. The hurdle value was this for both cases, and we had a huge F from data. Great. Okay, so not that difficult of a test, but keep in mind, be very careful, as I mentioned before, when we're testing means, when we're testing variances. So read the problems carefully. So that is it for chapter 6. So we described statistics before as the boring statistics with mean, standard deviation, calculating those numbers. Then we said there's some interesting stuff where we did confidence intervals and hypothesis tests. And so now we're getting into the exciting statistics part of the class. It just builds to this big crescendo at the end of the class. And that's probably not the best introduction for what I'm going to do now, which is a lot of talking. So anyway, so now what we're going to do is we've already talked about, okay, how do you do these statistical tests? And those are the foundations of everything we're going to be doing when we're handling data, especially the hypothesis testing stuff. We're going to think about things in terms of hypothesis testing, and you should, from now on, whenever you're in lab and you get results and you want to say something about those results, you should feel that you're on the hook to say, is this difference real, or is it just, can it be explained by the noise? And you have to prove that it's real, if you're going to say that it's real. Does that make sense? So you might get a mean here that's bigger than a mean here. But is that difference explained simply by random variation, the noise in your data? Right? You have to do that from here on out. So now, that's what we've done. That's where we've been. But now we're going to get into, before you get into the lab, how do you sit down and plan out the experiments you're going to do to make them as efficient as possible? So the people that developed these techniques have proven that these are the most efficient way to do experimentation, a certain type of experimentation. So if you're like me and you don't like to do a lot of extra busy work, then this is the stuff that gets you there. So this gets you the most information from the fewest number of experiments possible. So very neat design. So what we're going to do is first just talk about designing experiments in the general sense. So I'm going to go over this pretty quickly, and I expect you to read all the handout, but I'm not going to talk about all the handouts. I don't particularly like reading off slides. I don't think you guys do either. So first thing that we have to say is there are good strategies for doing experiments and bad ones. Almost goes without saying, right? That there are some ways you can go in and do a bunch of experiments, and that's not good, and other ways that are better. So what are the things that you think would go into deciding what makes for a good strategy or a bad strategy? So what would you want out of a good strategy? What would a good strategy for experimentation give you versus a bad one? Or think about another way. If I'm comparing these different experimental strategies, what criteria am I going to use to compare them? So what might be some criteria that we would use? Yeah.
Just having one variable.
Pardon?
Just using one independent variable.
What do you mean by that?
You're only
Only changing one thing. I'm really glad you said that. Only change one thing at a time. That's what I think you mentioned, right? I'll put a question mark there. So we're going to talk about that in a little bit. I know that's exactly how everyone's been taught. What else? What else might be? Yeah. All right. So time, you could put money, resources, right? What's another thing? So how much the experiment costs? So all those things we could say, how much do these different experimental campaigns cost? What's another really important thing? What would you want out of the experiment? So if you have one that's a low-cost experiment, one that's a high-cost experiment, sometimes the high-cost experiment might be better because what might it do? More precise, more accurate. That's an E. I could generalize those in they fulfill their purpose, right? So there's more philosophy stuff. The end is the fundamental principle of order, right? They're directed to the end. You know it's good because it's directed to its natural end. You guys should resonate with this stuff more when we talk about philosophy. But anyway, okay. So it fulfills its purpose, right? That's how we determine if something is good. So an experimental campaign that we're doing these experiments to answer some question. And so that experiment better answer that question. And the details about that is, in order to do that, generally it has to be pretty precise, has to be accurate, and so forth. So we talk about it fulfills its purpose, its end, and we do that as efficiently as possible. So we minimize the resources that go into it. So I think you could add safety in there, but we could probably categorize almost all the responses in those two camps. Maybe there's a couple others, but those are the big ones. So good. So that's what we're going to do. So then how do we evaluate those? All right, so how do we make sure we're answering the question, we're meeting the objective of our experiment, and we're doing it as efficiently as possible? So the one, as I mentioned before, I'm going to jump over a lot of this stuff. This one right here. Okay, so how you've been trained. I hit the wrong button. Okay, so how you've been trained is what I call the one-at-a-time method. So let's think about the the typical experiment we do. We think about chemistry lab, you're doing some reaction, and you're saying, I'm going to measure some thing about the reaction, either the yield or the conversion of some species. We're going to measure something, probably a yield of desired product in this reaction, and I'm going to vary just those standard things. I'm going to vary the temperature that I carry the reaction out, maybe the pressure if it's gas phase reaction. I'll measure the time or the residence time of the reactor. I might measure the concentration of a particular species. I may put a catalyst in there or no catalyst. So I could vary all these things, and I'm interested in seeing, okay, which ones of these things that I've just written, which ones really impact the yield. So think about this. This could be a very real situation. You're tasked with, hey, you've got to optimize this, and you start talking with other people, and you come up with a laundry list of, well, these are the things we think might do that. These are the knobs that we can tweak to optimize the yield. So now, you go into the lab. How do you go about doing this? How do you go about testing the effects of all these factors, I'll call them, on the yield, the thing we're trying to optimize, which I'll call the response? So the way that you've been trained is, and it has its advantages, is to say, I'm going to hold that constant, and I'm going to vary the temperature. Then I'm going to hold the temperature constant and everything else, and methodically vary the pressure. Right? So why you've been taught that is because, well, that's better than just randomly changing all of them, right? So you can actually figure out what the temperature did or what the pressure did. But what we are going to get at in this class is we're going to do better than this method. So that's kind of the state of things now. That's the way you've been trained. That's the way almost everyone does experiments. But now we're going to use a better method that's more efficient than this one-at-a-time method. So that's why I say it's good for some very unusual circumstances. Not going to go into that much more, but here's an example of just a similar type situation where you're looking at yield of a reaction. Here they varied time and temperature. So one way to do that would be, let's set the time. Let's pick a time, 10 hours. Let's vary the temperature, and let's measure the yield. Again, we've been calling that our response. We're going to use that. Y doesn't stand for yield, but Y for us from here on out is going to stand for the response. And that's the thing we are trying to optimize. And we're going to optimizing it by varying the factors, we'll call them. And these we're going to say are x's. Say x1, and there's a factor x2. So we might do this in the lab. And we hold time constant, vary temperature, and we say, okay, the maximum yield is somewhere between 230 and 220. We might arguably say, well, 220 is about the same as 230. Lower temperature is generally better. Let's take this and pick that as our winner, 220 degrees, and then we'll start investigating the time factor in the one-at-a-time strategy. So then we're going to set 220 degrees as our reaction temperature, and we're going to vary the amount of time that we let this thing go. So that number is the same as that number, should be. But then we say, okay, 8 hours seems to be the best that we can do. We get about, I think it ends up being about 86% is the yield. So there's our winner. And that's how almost everyone optimizes these multi-factor systems, these multivariate systems. That seems logical to you, right? It's probably what you're trained to do, what almost everyone is trained to do. So, but what my job is to convince you that is not always going to give you the optimum value. In fact, more often than not, this will fail. So if we really look at the real situation, so here's what we did. We set, what did we do first? Set time first? Yeah. We set time is equal to 10 hours. Okay. And we did these experiments. Then we picked 220 degrees. We did those experiments, and we said that was the best one. So I put this on a contour map where here's factor 1, here's factor 2, and then the numbers here represent the yield. You've seen these contour maps before, right? Do any hiking, sort of elevation type stuff? Okay, so obviously what these numbers represent is the real situation in this reaction. So our experiment optimized the value of 86% at these conditions, but we missed the real optimum, right? The real optimum value is right there. So the real optimum value is above 95% yield, and we're going to get there at about 235 degrees at about 5 hours. So if you're working for a company and you're here and the competition is there, keep your resume handy because you're going to be looking for a new job soon. So companies fight to get increases in yield and selectivity of like 1% is huge. So this is a huge jump. This is a huge miss if you're running your process at 86% yield, and if people are running at above 95% yield, they are going to beat you. So how do we get this? What we're going to do in this class is we're going to do the experiments that give us this contour map. Right? So you'll be able to produce this contour map, and for this case we could do this in 9 runs. We'll show that later. And how many runs did we do here? 12, maybe 11 if we didn't repeat that one. So in 11 runs, doing this one at a time experimentation, we didn't even get close to the optimum value. Then we could get this whole map that will show the optimum value and how stable it is, and we could do it in 9 runs if we have a better strategy for doing experiments. All right, any questions on that? So that's what, yes, Derek.
So this contour map, you determine that based off extra data, right? Not just off of the
Yes, yes, this is an example. You can imagine what you can do is you can put in your model of the reaction into Excel, and then you can model this situation, what results you'd get, and then you could display the real model, which would give you that. Okay, so why did this happen? Why did the one at a time experimentation not work? Is the very common situation is what happens when time and temperature, you have these two factors we say that they interact, which means when I'm saying, well, what's the best time to run the reaction? When I say there's an interaction, that means that depends. It depends on the other factor. It depends on temperature. So the best reaction time depends on what temperature I'm at. And we could flip it around and say the best reaction temperature depends on how long I'm going to run the reaction. And when you do one at a time experimentation, you miss those interactions because you only set time at one value, and then you vary temperature. Then you flip it around and you set temperature at one value and you measure time. So you miss these interaction effects. We're going to talk a lot about those later. But if you're wondering why this doesn't work, that is the reason. Okay, some definitions then. We've already talked about some definitions. Talked about the response. This is the guy we're trying to optimize. And we're going to always call that Y. So make sure you get these terms down, otherwise you'll be lost. So we're trying to optimize the response, which was reaction yield. What are we going to change? What are we going to vary to try to optimize that response? These are called the factors. They're the x's. They are the independent variables. So x's are the independent variables. We set those in our experiment because we're trying to figure out how do those x's impact the y. How do those factors, temperature, pressure, reaction time, how do they impact our reaction yield in this case? Okay, a run is we change a factor and we measure a response. So I think that's pretty straightforward. An experimental run is what you're used to thinking about an experimental run or a trial. And so one thing it's not, though, it's not just letting the process go and you're observing it. You have to control or set the X factors. So that's the difference between a controlled experiment and just taking data as they come off the process. Okay. Experimental unit, we're not going to talk much about that. We've talked already a little bit about background variable, lurking variables. Sometimes I've called them nuisance variables. And so these are the things that add noise to our measurement. And our measurement here is y. Right? We're measuring the thing we're trying to optimize, generally. And so these are the guys we're trying to control. So we did pair t-tests before to try to control these background variables or lurking variables. We will flesh that out and get some more tools to use to try to eliminate noise from our design. Speaking of design, an experimental design is just what are the collection of runs you're going to perform. Right? So how many runs are you going to perform? What are they going to look like? So in that example, this is how those definitions look. So we varied time, we varied temperature. Those things were the factors, the independent x's. We were interested in optimizing the yield. That was our response, the y values. And then if we pick one set of x's, one time, one temperature, that produces, we go run that reaction, we measure response. That is one experiment. But if we look at the whole set of how we're going to change x's, that's our experimental design. Does that make sense? So then this is the thing we're really going to focus on, is how do we design this, right? So how do we choose the x's in the best way? Okay, very briefly, why we do experiments is a pretty important thing. So if you think if you're out there in industry and you are dealing with some sort of process that's making something, you can get tons and tons of data by just going into your process logs, and they measure a bunch of stuff, and you can go on Excel, you can do all sorts of regressions and see which things are correlated with the response you're interested in optimizing. It's an easy thing to do, but it doesn't give you a lot of information. So why doesn't it give? We call that historical data. So it's not a controlled experiment. You're just sitting there passively measuring stuff. Right? Why doesn't that work very well? Is you're just making correlations. We've talked about correlation not being causation here before, right? So I'm clear on that. I don't want to skate over that too fast because that's a very common error that people make. These two things are correlated, so A is correlated with B, therefore A causes B. Right? That's wrong. So there could be some other things, C, that impacts both A and B. Happens all the time. So hopefully I think we've talked about that before. So that's a problem. You're just doing correlations. You're not determining what causes what. The factors, right? These are the X values, our independent values. They might be correlated, which means if we're not controlling them, temperature might be high when pressure is high, and temperature is low when pressure is low if we're just doing historical data. And if those two things always are changing together, there's no way you can determine what temperature is doing apart from pressure. Does that make sense? If you have two variables and they're always changing together, you can't separate what each of them is doing. We say they're convoluted. What's another? Or we also say they're confounded together. That's the word we'll use most often. So they're confounded, but in an experiment, we set those, we control it. So we make sure that we break that confounding apart. We set a high temperature and a low pressure, and we set a high pressure and a low temperature, that kind of stuff. We'll talk about randomization before these other things we'll talk about later. I'm going to go through that kind of stuff. You guys can read that. Spend a little time on this slide right here. So this is our map of what we're going to be doing for the rest of the class. So these are the experiments, or the different sections of experiments that we are going to do. We're going to be doing these 3. So generally, how you approach something, you've got some problem you're trying to solve. You get together with operators, all these different people that know something about the process and the problem, and you brainstorm and you say, how do we fix this problem? And you have this laundry list of things that they think might be solutions. Then you have to say, all right, I've got this list of 100 things. Which ones are worth testing? So you talk amongst yourselves and you get down to a list of maybe 10 or 12 things, 10 or 12 factors that you think might be important, right? They might, by important, we mean you have 10 or 12 X's that will impact your response Y, which is the problem you're trying to solve. So your first job then is to take that large number of factors and reduce it down as efficiently as possible. So 12 factors, that's a lot of things to change. So you're going to try to trim that number down. So one set of experiments that we are going to use, one category, is designed to how do I trim the number of factors down to something more manageable, something I can handle. Once you do that, you take that smaller set of factors and you study it with a linear model, and you get more information from that, and then depending on the situation, you might stop at this second stage. If your linear model is good, that means Y is a linear function of your X's. If it's not, if there's nonlinearity, right? If you've got to model some curvature, you need to go get more data, and that's in this third set. And then in this third set is where you can make that nice, pretty little contour plot like we just showed for that example. Okay, so, and that's the order we do it. We do screening, we do this constrained optimization, and then unconstrained optimization. That's the way it happens in the real world, but our job isn't necessarily to do that right now. Our first job is to learn it, and it turns out, pedagogically, it's easier to learn this one first. So that's what we're going to do. We're going to learn the second step first, and then once we know that, then we're going to jump back and learn the first step, and then we're going to jump ahead and learn the third step. Right? So that's the order we're going to take them. So that's going to happen starting tomorrow. We're going to start learning how to do that second step when you have a reasonable number of variables, and you're really looking at particularly what are they doing and what interactions do they have. I don't know why I have this in here, but I guess you can read it. I once was diligent about putting Dilberts in my presentations, but I really don't know why I have that particular one in there. So, okay. All right. All right, I can do that. Okay, I'm jumping ahead. This is the last thing I want to talk about here. We got just enough time to talk about it. This is pretty important. This is a pretty common mistake. So I remember I started telling you this story at one point, but then I stopped. And so had a graduate student once, and we were doing research on measuring mercury. I think, yeah, Jeff's heard this story before. So we were measuring mercury from a reaction. We were looking at different catalysts. We were doing time, temperature, those sorts of things. And we were trying to figure out, okay, what catalyst does the best job in reducing mercury? Mercury's really hard to get a handle on. It's sticky stuff. It's hard to do a mass balance. So, and each experiment would take several hours or days to perform. So I'm at this guy's thesis defense, and let's see, we'll call him. Let's see, we'll call him a name. We'll call him Wai-Peng. So you don't know. So Wai-Peng was at his thesis defense, and he had confidence intervals on his results. And he had really, really, really tiny confidence intervals. Really tiny. And all the faculty members in the room had done some mercury work and know that there's just no way when working with mercury and trying to measure it that you have any confidence intervals that aren't just gigantic. So it's really hard to discern any signal from noise. So we asked him, like, Wai-Peng, how did you get such tiny confidence intervals? And he said, oh, you know, I took my data and I used the statistical formulas and out came the confidence intervals. So what he did is think you have a reaction running and you have an online analytical device that's measuring the reaction. Okay? So you've got a reactor in here, packed bed reactor, you've got flow in, flow out, and you say you can measure it with it wasn't a GC, it was a mercury analyzer, but there's a GC underneath that red thing back there. A GC or a mass spec, something that's measuring it over and over and over again. And so he's measuring the concentration of something. Concentration of reactant starts here. We kick off the reaction, it drops, and then it goes like that. So time, and so concentration of a reactant. Does that make sense? It drops, reactions consuming the reactants. Everyone that's not, all you mechanical engineers, is that okay? I know you love chemistry, right? So when I look at that, is he charged the reactor once with a catalyst, he started it up, and he got to some steady state value. I would say that is one data point. That is some change in concentration. You can get a reaction rate out of that, and I would say that's one data point. Does everyone buy that? What Wai-Peng did is he took every data point that the machine was collecting, called that, added those together in N, and had about 1,000 N's, 1,000 data points down here. And when he calculated X bar with S over square root of N, he got a tiny confidence interval. Does everyone understand what he did? And you can kind of understand why he did it, right? He had all this data. So what these are just repeat measurements. What the whole thing is a repeat experiment. So to get at this, we have to think about what's the source of error? Is the source of error just in your measurement device, or is the source of error loading the catalyst bed, getting the flow stable, all these other things that go into a repeat experiment? We'll have to circle back and talk about this next time. But what I want you to think about in our Wednesday cliffhanger is how is a repeat run or a repeat measurement different than a true experimental replicate that we could count as a different N? It's not as cut and dried as you think. So think about that. Print off the DOE 2 notes. We're going to get into that almost right away on Friday. Come to the Burns and McDonald thing that's happening 3 o'clock on Friday. It'll be in Westerman 105. I'm going to send out an email directly. So if you want it for internships, Burns and McDonald, so they are very competitive to get those internships, but they're coming to talk about their program Friday.